Oh no, it's not staying in there.
Discord is not sterile.
Okay. All right. Don't bump the camera tripod.
Thank you, Sarah. Do you want to explain what's happening to the fans, Alex? I mean, they probably know. They probably figured it out.
Yeah, but
What's happening to the wets?
That's true.
What's happening to the wets?
what's the situation?
Well, I can tell, like, just what's happening with school and stuff.
I don't need to explain it to anybody. It's happening all over the goddamn world. We're going to be totally online starting after spring break. So no more videos till after September. March 30th. And it's not even clear whether they're going to cut out a week of classes and not paste it back in at the end or what. I don't know if I'll be able to cover everything, which really sucks. But there's a lot of questions that still have to be answered. But there's no substitution for as joyous as this occasion is, so it really, really, really pisses me off. But anyway.
Do I still have a job?
Yes, if you are an employee of the school, you will have a job and duties as TAs and so forth, so that will still stick around.
Someone put that
Homework
in the
quizzes?
group chat.
Huh?
Homework quizzes? Yes, no?
I have not figured that out yet.
Okay.
I don't know what I'm going to do. It might be easier for you to just do your homework, scan it, and send it to me or something like that, or we just say fuck it and we meet anyway. I don't know. I mean, how many of you are going to be around? I don't know. Okay, let me just get on. We'll talk about this maybe at the end of class. I got to get onto some physics right now because I've been talking for the last hour at a faculty meeting about coronavirus problems, and I just want to do physics for a minute. Okay. So as we talked about last time when we talked about the golden rule, there is in each of those golden rule expressions a single factor m, which actually encompasses the dynamics associated with the process that you're trying to study. And I told you last time that actually calculating m requires us to employ the Feynman rules, and so we're going to explore that today. And today, I'm going to get you through the Feynman rules actually, and we'll do some calculations, but it's going to be entirely in terms of a toy model called the ABC model. And the ABC model is going to give you sort of the robust features of the Feynman rules, and then as you might normally guess, as soon as we drop spinners back into the story, it gets a little bit more complicated. So we're going to look at a really simple version of it today, and then next time we'll bring the spinners back and we'll do it for real, okay? So here we go. So we're going to work with a simple toy model whose Lagrangian is given by the following: 1/2 d mu phi a d mu phi a minus 1/2 mc over h bar squared phi a squared. And yeah, I'll just do it this way. So we're going to write this down 3 times with phi a, phi b, and phi c. Okay, so what have I got so far on the board? Please tell me, is Hunter here?
He's on the Discord.
No, sorry, the wrong Hunter. Hunter's on here?
Hunter Thompson is.
Hunter Thompson is on here.
Yeah.
I see Avery blowing his nose, I see me pointing at the screen, and then I see this. Huh? Okay, screw Hunter was. I'm technologically horrible.
This took me a horrifically long time to
Chance.
figure out.
Is Chance in here? No. Oh, yeah, you are. Yeah. Okay, What is this describing?
Lagrangian.
It is a Lagrangian describing what? Are these spinors or scalars?
These are scalars.
That's one of the reasons why this is so simple. Are they interacting at all?
No.
No, yeah, these are just the kinetic terms. This is the derivative term, and this is the mass term for each of the three fields, okay? Now, that's of course an extremely boring theory. We just have particles A, particles B, particles C, and they're not talking to each other. We want them to talk to each other because that's where the heart of these calculations comes from. That's what dynamics is. It's the forces that things exert on each other. So we're going to give them an interaction, and the interaction is going to be pretty simple. It's just going to be a term composed of a product of all three fields, okay? So some important features of this model: three real, spin zero, and we now want to shift to the language of particles instead of fields, because what we're going to be working with are the small fluctuations in the fields which correspond to particles. So I'll just refer to them as particles, and they'll play more of a particle-like role in the calculations and the Feynman diagrams that we draw. But we've got three spin zero scalar fields. Here's an important observation which you'll appreciate much more when we add spinors to the story, but I need to go ahead and make it now. They are their own antiparticles. So what I mean by that is that the antiparticle, which I would normally designate as a barred object, is equal to A itself. And what that means in a Feynman diagram, and I haven't given you a Feynman diagram yet, but I will in a bit, is that if I have a particle A which is moving along, I will not put an arrow on the line. We'll put arrows next to the line later, but when we later introduce spinors and you have to distinguish particles from antiparticles, when you have a spinor field, you have to put an arrow on the line, because an arrow going forward in time means this is a particle, whereas an arrow going backwards in time means it's an antiparticle, and you have to distinguish which one it is. You don't have to distinguish particles from antiparticles in this case because they're the same thing. So when we want to talk about a field or a particle propagating, we just draw a line with no arrow on it. That is separate from specifying the direction it's moving, momentum. The momentum will always be forward in time, okay? And that would be like a little arrow below it, something like that. But if you put an arrow on the line itself, that's telling you whether it's particle or antiparticle. Since these are their conjugates, then we don't have to worry about it. Now, one feature of this which we will make use of is the idea that the mass of A is larger than the mass of B plus C, because that means that opens up the door to looking at the decay of A into B plus C, all right? And then 4 is the following. The interaction vertex I can just draw as an A line intersecting with a B and a C line. And if you squint your eyes and think about what would you draw for this interaction, it would be an A, a B, and a C all coming together at a point and having an interaction. Okay? Notice, is that allowed? No, I mean the interaction is phi A times phi B times phi C. This is not allowed. Okay? Only this is allowed. And we'll find similar arguments when we actually throw spinors into electromagnetism and do all the nastiness associated with that. Okay. And I have to say, like, if you've never done this before, it's actually rather interesting. And it's really just a cookbook for how to use Feynman diagrams to calculate these things. Yes?
So the other case you drew where we had an A and two B's?
Yeah.
That would be if we had like phi A times phi B squared?
Yes. So if we added interactions and we included an interaction of the form like that, or if we added an interaction of the following form. this term would allow A, B, B, and this term would be like so. So you can literally just look at the multiplication of things and immediately determine what the interaction vertex looks like. So in this story, we've only got one. It's an A line, a B line, and a C line all coming together. Okay. What we want to do now is we want to pick a process, and this should be utilizing the ideas that we talked about last time, but we want to pick a process, and whether we're trying to calculate gamma I for the process or sigma I for the process, it doesn't matter. In either case, we need an expression for M, okay? So you can think about these two things both operating on MI for that process. So if, in case you don't remember, like if we're calculating the decay rates, we might talk about A decaying into B plus C, or A decaying into D plus E, et cetera, et cetera. These are indexed by I. Okay? Or we talk about the scattering and the scattering cross sections, but in each of these you'll have a different expression for MI, and I'm just showing you how to calculate it. So we want to pick a particular thing, so why don't we look at that one. A goes into B plus C, and ask ourselves what goes into this calculation, okay? Now I'm not, again, this is not a course in quantum field theory. I'm not going to derive where all this comes from, and in fact, to do the calculations, you don't need to see the derivation. You just need to see the rules, work with them a bit. Once you get familiar with them, they're pretty straightforward, okay? So we want to start by analyzing the decay of A into B plus C. First of all, could we even analyze the decay of B into A plus C? Is that allowed? Sean? Sean here? No? Brandon, are you here? Damn, where is everybody? Anthony. Oh, there you are, sorry, it's the hat. Anthony, can B decay into A plus C? No. It's a good guess. It's a good guess. No, why can't B decay into A plus C? Anyone? Yeah.
It's because the mass of because the mass of A is greater than the mass of B plus C. Oh, I didn't see.
Yeah, remember the mass of A is bigger. So this is somehow gaining mass. Yeah, okay, all right. Okay, so here we go. First of all, decay of A into B plus C is going to be our first example. We draw the following diagram. A goes into B plus C. I did not connect those, you notice? Because it turns out that even though there is an obvious and simple way to connect them, that is not the entirety of the story. So normally the way we would pictorially do this is we would just draw a big bubble here and just kind of fill in with foggy haze. And M M gets contributions from all possible ways of attaching the internal or the incoming and the outgoing legs of this diagram. And I should say that in the convention that we're using, you should understand time to flow to the right. So I call A an incoming and B and C an outgoing. This is important because some particle physics texts instead employ the convention that time runs up. So they would draw something like this. Okay, but we employ time going to the right, so your incoming stuff is on the left and your outgoing stuff is on the right. So what are the contributions that contribute to this? Well, first and foremost, there is the diagram that everyone expects. Okay? We will learn how to calculate a contribution from this term to this quantity. Okay? But there are more. For example, I want you to try and figure out how to finish that in your notes. Write down. How many vertices do you see in that diagram? 3. You need to use this 3 times. A, B, and C coming into each vertex. Can you do it? Who can do it? Come on up.
Which one of us?
Gabriel.
Okay.
Ross, you'll come up and do the next one. You'll come up and do the next one. Good. Yeah, perfect. See, it's not that bad, is it? Notice, A goes to C and B, A goes to C and B, and A goes to C and B. He's using the same vertex.
Do we not have to worry about the fact that this sort of makes it look like B is like going into A and C, or C is going into A and B?
No, you don't need to worry about that, and I'll explain why in a few minutes.
What does a vertical line represent according to time in this case?
Okay, so the vertical lines, so if it makes you feel any better, you could draw this diagram like this.
Okay. So it doesn't mean anything.
But these lines, these 3 lines here, not this one, or this one, but the 3 that form the triangle are all going to be associated with virtual internal particles. And interpreting their motion as forward and backward in time is irrelevant. Okay? We can't see them, we can't experience them, but they do contribute to this amplitude. But you won't have to worry about whether you're trying to interpret as going forward in time or backward in time. And that's going to play a similar role when we actually have particles and antiparticles, because we dump spinors into the story. Okay? Is that the only additional diagram? Hell no. All right, we've got this one. Ross, come on. Why you guys are sitting in the goddamn back of the room? I know, you're worried about my health, but that's fine. Draw it. Finish it up.
You get this, you will die.
I know. Hey, man. Go ahead.
So this is gonna have to be A.
Yes, that has to be A. Yes.
But then in this bubble, are you just saying that anything can be in this bubble, or?
Well, no, you've got 2 vertices, and they have to be built like this. There you go. Good job. Good job.
I thought
Thank you,
it
Ross.
was a black box.
Nope, yeah, no, it's not a black box. Okay?
Does it matter which one's B and which one's C here?
No, you can make this C and this B. That doesn't matter, and it won't impact the calculation at all. Okay? How many vertices do you see on that one? 3, exactly. So it turns out that there are 2 more contributions to 3 vertices. Here you go. Is that all? Where do you think we go to next?
I think you could make like any number of bubbles that you wanted.
What can we go to next? 5 vertices, not 4. Yeah, think about it, you'll realize, yep, to insert only these interactions, you gotta double, you got, not double, but you gotta bump it up by 2. So this is the lowest order diagram. This is the 4 next to leading order diagrams, and then the number of diagrams that have 5 vertices is way bigger, and then it just gets bigger and bigger and bigger and bigger and bigger and bigger. Okay? Now, this story is infinite. But here is a very important observation. We'll learn this in a minute, but I'm going to go ahead and say it because now is the important time to tell you. Every time there is a vertex, you must write down a factor of the coupling, G. Right? I mean, that should be part of the calculation because I've got these three things interacting. So G should play a role in M, okay? But if I have a G in this one, what do you think I'm going to have in this one?
3G
G cubed. 3G is not that important. A coefficient times G is not really enhancing G. Okay, what about to the fifth? Or 5, yeah, 5 vertices is going to be to the fifth, okay? So,
That isn't reassuring, that just makes me think that the more vertices you get, the more this blows up.
exactly, unless what?
G is less than 1.
For G less than 1,
Trick this one.
then which of these is the biggest?
G.
Just G. This is an expansion in G. Okay, it's called a Feynman expansion, and it's just like using a Taylor expansion to try and approximate the answer to what is f of some f at some value. Okay, in that case you're taking derivatives, but it's the same story. As long as you're expanding in a number which is less than 1, the lower order contributions are larger. All right? Well, the good news is when you're doing electromagnetism, G is less than 1. When you're doing the weak interaction, G is less than 1. When you're doing the strong interaction,
Maybe it's not.
it depends. Sometimes G is less than 1 and sometimes G is equal to 1. We'll talk about why G changes later. But for now, the important power of this is if you want to know M, you start with the simplest diagram. That's by far the easiest one to calculate. And then if you want to improve your answer, you include the next order. All of these. Don't just do one and leave out the other 3. And then if you want to bump it up to order 5, which you can, you'll do the 5th order. Okay? So this is what form of analysis? It's perturbation theory, exactly. Okay? So, with that in mind,
Alex, what's perturbation theory?
yeah, so perturbation theory is, so I would say in words, and there's many different formulations of perturbation theory, but the idea is that you start with a free theory or a very simple solvable theory. You know that we can solve the free form of this theory, right? Because if we hide that, then you can find plane wave solutions to this, for example, okay, to all the equations of motion. So you normally start with a free theory or at least a solvable theory, and then you introduce interactions or modifications to the theory. Governed by a small parameter, G. So for us, the dominant answer is the free theory, and then if we introduce interactions and they always come along with this small number, then you can actually calculate the interaction contributions to the answers to questions and ignore the higher order terms, okay? It's not just free theories and you're introducing interactions. You could just take a solvable theory and introduce a modification to it. As long as the modification isn't very big, then you can often expand it in the parameter of the modification and you can take your answer from the first few terms. So that's the spirit of perturbation theory, which you're supposed to learn at some point in getting your degree. Did you? God. You had one day of perturbation theory?
And it was optional.
Oh,
At the end
Jesus.
of one.
Okay, well, you're going to have like 4 or 5 days of them in here. So. Now, it's not going to be the same sort of story. Okay, so let me give these names, and then we're going to actually dump into the rules for how to calculate these. So this is what's called the tree level order. And it's a tree because it ain't got a loop in it. Trees don't have holes in them. Some trees do, those are special trees, but trees are always the contributions which don't have loops. And I know these are circular loops, but that's also a loop. A loop is just a closed internal path, okay? So the tree level contribution has no loops. This guy is called a vertex correction. And you don't have to memorize this language. I'm just giving you some indication of the language that goes with these. And this is vertex correction because really and truthfully, you know, you see A, you see B, you see C, and then it's like somebody took that dot and they blew it up into a triangle. Okay, so it's another way of modeling the vertex. However, these three diagrams, it's more like, you know, this is just A, B, C right there. So this is more like a modification of A coming in, it burps, it goes back to itself, and then it just does the BC interaction. And similarly, this is B burping and this is C burping, okay? So these are often called self-energy corrections.
Why are they called corrections?
The corrections are just, they're bringing in more possible forms because of this G interaction. They're giving you a more, this, if you add these to what you get from this one, the answer is more correct. That's largely why we use the word corrections. Yes?
How does B perfect to A if A is more massive than B?
That is an interesting question, and it is something which I will pinpoint in a bit. But yeah, that's a concern. Like, how did B turn into A plus C? That's an interesting question, and I will come down on that in a minute. I promise. Ross?
I guess like with the interaction term, if we go back to Lagrangian, it seems like that in order for the interaction to take place, all three fields have to already be there, in a sense.
They all have to be there?
Because like if we were to set like phi B and phi C to 0 initially, then it doesn't seem like they'd interact. But then I don't know. Well, I guess what I'm saying is like with these diagrams, it doesn't seem like that B and C could just emerge out of A on their own, unless there was already like some underlying B and C contribution there.
This is exactly what's happening in this process. B and C are emerging from A on their own. I don't understand.
Oh, I was referring actually to the Lagrangian.
Yes?
And the interaction term is G, phi A, phi B, phi C.
Yeah.
So if you set phi B and phi C to 0, then the interaction term goes away.
Why would you set it to 0?
They don't exist.
Are you setting them equal to 0 for all time or on the initial time?
Or just initially.
I am not sure how to answer your question right now, but let me plunge ahead because we got to get through these rules and get some diagrams calculated, but I'll think about what you asked. Okay, so I'm going to write the rules here so that I can keep them here, and then I'll do some examples over here. But here we go. And I promise these calculations are not going to be that bad today. Maybe next time. Okay. Calculating MI. And again, the I index is just, well, it's actually super complicated, right? Oh my God, it's terrible. Because I said that if you want to know about how A can decay, well, this is one route, but there are others. You know, you can have A decay into maybe B. Well, actually, in this theory, it turns out that's the only one. But you could have different outcomes of a decay, and we label those by I. But then if you focus on only one outcome, then you have to label all these. Okay? But anyway, each of these gets a contribution to the M. And so I'm going to calculate the M for this one, the M for this one, the M for this one, et cetera, et cetera. Actually, I'll calculate one or two, and I'll let you do the rest. So here we go. Step one, label all momenta. with either pi or qj. All right, and you're going to do this with arrows next to the lines. So actually, I'll walk you through an example of this calculation as I go through each of these rules. So the first contribution I'm going to calculate is just this one. Okay? So I need to label the momentum just next to each of these. So I'm going to call this P1. I'm going to call this P2. And I'm going to call this P3. Okay? Why didn't I use Q? What do you think Q is reserved for? Yes, the Q is reserved for the virtual particles, okay? This diagram doesn't have any virtual particles in it, so we don't have any Qs. Now here's an important distinction. Remember, time flows to the right, so the momentum of this particle must be going forward in time, so too the momentum of these particles. However, when you have internal particles, so I'll just draw an example. So for this line, you need a momentum. For these lines, you need momentum. And those are external momenta, so I use P. For this, I use Q, and I can do this. Or I can do this. Or I can do this. It actually doesn't matter how you direct the internal momentum, and you'll understand why in a bit, okay? But the external momenta, or sorry, this is actually a Q as well. My apologies. So I could actually do it that way. This is an internal line. Everybody see that? These are the external lines. This is an internal part of the story. Okay? So the internal lines get Q labels, the direction doesn't matter. The external lines get P labels, and they always have to be essentially pointing forward in time, and you would never do an external particle vertical. Okay, because you can't figure out whether that's forward or backwards in time. Do you have a question? Okay. All right, so the next step. For each vertex, write down minus I times G. Okay? So, how many vertices? Yeah, this is not hard, guys. I told you this would be pretty straightforward. How many vertices? One! Yeah, so I write down minus IG. Boom. Okay? Step 3. For each internal line, we write a factor of I over QI squared minus MI squared C squared. Okay, where this is the imaginary number, and then this I, well actually I'll do J as a label for it, but anyway.
Because that way it doesn't matter whether Q is positive or negative, because it gets scored.
Yep. Okay, and it's worse than that for the next rule. Okay, so how many of these lines do I have in this diagram? How many internal lines are in that diagram? 0! Yes, so I don't write down any of these. This was a pretty easy example. 4. Oh, yeah, sorry. Let's pause for a moment and discuss this. Talk to me about that denominator. What is Q representing? Stephen. Where's Stephen? Joseph. What does Q stand for? 3 momentum or 4 momentum?
I want to say 4 momentum
Okay, yeah, so this is the form momentum. So I have a particle, I'm squaring its form momentum and I'm subtracting its mass squared times c squared. What is that?
That's very bad.
What is it?
I mean, it seems like it should be zero.
It-
Because
Yeah, so this is the mass shell condition that this equals 0. So why don't we divide by it? Sure, why not? That'll make m really small. Okay? What we discover is that internal particles need not satisfy the mass shell condition. They don't have to satisfy this. That is, of course, why when there were situations where you had B going into A plus CB and people were coughing about B can't decay into A and C. Well, if you're going to disregard the mass shell condition for A and C, you can definitely have this happen. Okay? So we'll play with this more when we actually have a diagram that includes it, but for now, we'll just let that be. Okay, so step 4. For each vertex, we want to conserve form momentum. And this should be done in a manner very analogous to what we saw yesterday with Fermi's golden rule. Can anybody look back at their notes and tell me how we enforced the conservation of form momentum in Fermi's golden rule?
Is it direct output?
Yeah, we use a Dirac delta function in 4 dimensions. So we would basically include a 2 pi to the 4th. Let me actually bring this down.
Does this add a thing? Or does it multiply by 3?
Okay, so for each vertex, we want to write a term like this. Of course, we only have one vertex, so we'll only write one of these, so let's do it. Okay, what is the incoming momentum for that vertex? P what? Well, no, we just use the momentum labels.
P1.
It's P1, yeah, it's P1. And what's the outgoing momentum?
P2 plus P3.
It's that easy. Okay. Now, of course, obviously, if the external lines are connected to an internal bubble or something, then you'll have P's and Q's in here, but that's fine. And it doesn't matter what direction you pick your Q's. Okay. But you have to, we'll see an example of a Q-ridden situation in just a moment. So let me finish up with this one quickly, and then we'll see how more of these come into play. All right, and now comes the one tricky part. You're going to integrate. Integrate everything that you've written, that whole expression, over all the internal form momentum with d4qj over 2 pi to the 4th factors for each one. How many are in this diagram? Say it again?
0.
0. Do we have to do an integral? Nope.
And then
Pretty sweet.
just m, like that.
This is just m. M you have to dump into Fermi's golden rule and you have to do integrals. Okay? Step 6. After you've done these steps, you will have an overall, and this might seem like super obvious, but it's not going to be obvious in a bit, 2 pi to the 4th delta 4 P external total in minus P external total out. Okay, where this does not involve any internal lines, it just involves the externals, okay? Cancel this and multiply by I to get M, and you're done. Okay? Daniel. Where's Daniel? Oh, there you are, sorry. I'm kind of hiding behind Madison. Daniel. What is M? It's what? Oh. So, do you see this factor? In here. Do you see a 2 pi to the 4th times a delta function conserving the total momentum of the external particles? Do you? Yeah, it's this term times this term. So we want to drop that, and then we want to take what's left and multiply it by I. So what is M? It's G. Pretty straightforward, isn't it? Gabriel.
I have a question about the last step.
Yeah.
So we're multiplying by I, but why are we doing that? Because in the Fermi's golden rule integral, we have like a magnitude squared of M. So why do we need to multiply by I?
Because M is going to get many additive contributions.
Okay.
If you just had one diagram, multiplying by I wouldn't change anything. But you're always going to have more than one diagram. Okay? So now I'm going to work through one more example, and then I'm going to turn it over to you. So the next example I'm going to work out is going to be this one. Following these steps. Here we go. Now, one of the very important things, if you're calculating a single diagram, then it doesn't really matter where you put 1 versus 2 versus 3 versus whatever. You might wonder, why aren't you putting PA versus PB versus PC, right? Well, you've got more than one B up here in here. So if you label this as PB and this is PB, then which one are you talking about? And it gets worse because even though these B's are going to end up having to have the same momentum, you can certainly have diagrams where the particle B appears in multiple places and it can have different momentum. So that's why I'm indexing the momentum by numbers. Okay. So let me get some labels. I'm going to have P1 there. I'm going to label this P2. I'm going to label this P3. Those are all external momenta. If you're just doing one diagram, it wouldn't matter which one you call 1, 2, and 3. But if you're doing several contributions and you're going to add their M's, you need to make sure that if you're going to call this one P1, this needs to be P2 and P3 in all of the diagrams. Okay? Because you don't want to talk about particle B coming out with P2 here, but particle B coming out with P3 in a later diagram. Those aren't equivalent. Okay, so now I'm going to label my internal momenta. So I'll do a P4 here, or a Q4 here, sorry. Q4, and then, say again?
We're starting the Q's after the I's, or after the P's, so like we're starting
Yeah.
Q4 and after
Yeah, I don't like to repeat the indices. But anyway, okay, so I'm going to do that one to be Q4. I'm going to do this one to be Q6, and this one to be Q5. And again, it doesn't matter what direction you pick them. I'm just going to pick them in what seems like an obvious direction, although it's not entirely. Okay, are you ready? Oh, okay, good. I like it. Now, I want to stress to you, this was way easier than what I'm about to do. But what I'm about to do is not hard, it's just way more involved. So don't think that this is an example of what these are like. This is an example of what these are like. Here we go. How many interaction vertices are in this diagram? So step number 1, I write down minus ig cubed. Okay? One factor of minus ig for each vertex. Just go ahead and multiply them together. Okay? How many internal lines are in this diagram? 3. So I need this factor for each of them. I'll start with Q4.
Well, we have to write this with like that sort of, what is that, like the big pie, like a multiple.
I'm not going to do that.
Okay.
You would get to do that if you had enough of these, but honestly, this is going to be hard enough. So I'm going to do it explicitly. So Q4 squared minus, and then put in the mass of the particle that is involved with this internal line. In this case, it's B, so MBC squared. And then Q5 squared minus MA squared C squared, sorry, these are M squareds, times IQ6 squared minus MC squared C squared. Okay? That's just getting started. Then we have to multiply by conservation of form momentum factors at each vertex. Let's start with this one. So these are multiplied together. So 2 pi to the 4 delta 4 incoming momentum to this vertex. Outgoing momentum? Yeah, now it's outgoing Q4 because I drew the arrow that way. I could have drawn the arrow the other way, in which case it would be considered a incoming. Okay? Second interaction vertex is this one. What's my incoming momentum? Outgoing? And my last interaction vertex is this one. Incoming momentum? Outgoing? Good. Now you might wonder, why am I not just stacking all these factors of 2 pi to the 4 up and letting them just make one big 2 pi to the blank? Okay. We'll understand why in a moment. You want to keep these things separate. All right? We need to put down an integration measure for each of our internal momenta. And then remind ourselves that these are integrals. It's a little bit bigger than the previous expression, which wasn't even an integral. But let's do some integration.
Just because it's delta functions.
Exactly.
Just kind of thought it.
Yes. Yes, that's the only integrals. Listen to me. And I want to iterate this. In many cases, you will end up with a true integral without a delta function to manipulate. I'm not going to ask you to do a single one of these in that class. But you need to do all the integrals you can do with delta functions. Okay?
How do we end up with something that does not have a delta function?
You'll end up with this delta function which you erase. You'll see that emerge from here.
Okay.
Okay, so I'm going to go through this. I'm going to do all these integrals. All right, so there's different routes that you can take because, for example, you know, first of all, you got three delta functions. Which one do you want to use first? And when you use one, how do you want to use it? For example, I can take this delta function and I can say, okay, P1 is equal to P3 plus Q4. Or I can say that Q4 is equal to P1 minus P3. Okay, in either of these cases, the argument of the delta function is 0. But if you use this, then what that means is you go through everywhere and you replace P1 with P3 plus Q4. If you use this one, you go through and everywhere you see Q4, you replace it with P1 minus P3. You could try and say everywhere I see P1 minus P3, I'll replace it with Q4, but that obviously doesn't make sense because P1 minus P3 doesn't happen very often, okay? So I'm just going to go through one particular scheme, and here is the very beautiful resolution to this, which is not entirely obvious. It doesn't matter what you do. You'll always get the same answer. Okay? But here we go. So just to be able to copy my notes, so I'm going to start by using this delta function, Q5 plus Q6 minus P2, to do the integral over d4 Q6. So I'm going to set Q6 equal to P2 minus Q5 everywhere in this expression. Okay? So I'm going to do an integral, so I have two integral signs left, and then I just go through it everywhere I see Q6, I replace it with P2 minus Q5. All right, now you need to do this in the delta functions as well. I got no Q6 in the first one, so I'll just copy that one down. This is the one that I used, so this is going to vanish. And by the way, now you understand why I would keep the 2 pi to the 4s here and the 2 pi to the 4s here, because I'm doing the Q6 integral, so this whole thing goes away, and this 2 pi to the 4 times m goes away. Okay. So we've got a Q6 in here, so I'm going to place Q6 in that delta function with P2 minus Q5. Minus P2 plus Q5 minus Q5. Q5's in there cancel. And then we are still integrating over Q4, or 2 pi to the 4th, and Q5 over 2 pi to the 4th. Right? Everybody follow? What do we do next?
Same thing with one of those other guys.
Yes, yes, we're going to pick another one. So to finish this up, we shall, and again, you can do it in a couple of different ways. We're going to use delta Q4 minus P2 to do the integral of d4 Q4. And that's going to leave us with one integral of minus I g cubed times, okay, Q4 there is going to get replaced by what?
P2?
P2, yeah. So this is going to be I over P2 squared minus MB squared C squared I over Q5 squared. And now, just as a point of notation, there's only going to be one Q left in this story. So I'm just going to call it Q. I'm not going to call it Q5 anymore. I'll just call it Q. Over Q squared minus MA squared C squared times I P, P2 minus Q squared minus MC squared C squared times 2 pi to the 4th times the delta function And now all I gotta do is plug P2 into this, P1 minus P3 minus P2. You notice anything emerging? Yes. After this, you will have an overall 2 pi to the 4th times the delta function conserving the exterior momentum. There it is. So we drop that, multiply the thing by I, and that's M. Okay, and you don't need to do that integral. Don't worry about it.
You can do that integral with respect to Q5, generally?
Oh, sorry, yeah, I should have put that in. So yeah, this is integrated with respect to, although now I've just called it Q.
Yeah.
Sorry, yeah, I need my integration measure. Does this make sense? You sure it makes sense? Now, you know, there's a couple of subtle things. You can move this outside of the integral because it does involve Q. Okay? And then this is actually one of the key places where if you do this in a different order, this might end up being P2 minus Q, and then this would end up being Q versus P2 minus Q here and Q here. But those two expressions are actually equivalent. Can anybody tell me why?
Because A and C are, like, A and C are your two virtual particles, so it doesn't really matter which one you play on. Because those are those two factors, the MA and the MC.
So does everybody understand what I'm saying? I could say I over Q squared minus MA squared C squared I over P2 minus Q squared minus M, what is it, C squared C squared is equal to, well, I should say the integral of this is integral of P2 squared minus Q squared minus MA squared C squared I over Q squared minus MC squared C squared. Yes, Ross?
Oh, I was gonna say, the reason why they're equivalent is because you can essentially redefine a new Q variable as P2 minus Q.
Exactly. You're integrating over all possible values of Q. Okay? So you could replace the integral over dq with the integral over dq prime, where q prime is defined as P2 minus Q. I think that would work. But anyway, it doesn't matter. But you can basically, you can always shift the origin in an integral from minus infinity to infinity. Okay? And you need that detail because, I was going to give you a homework problem on this, but I figured I'd just explain it to you. Because that's the only thing that could appear different if you do the different route of what you use the delta functions to evaluate. That's the only thing that can appear differently, but they actually give you the same expressions. All right, so how do we feel? Good? Awesome. I want to give you some markers. I want you to break up into 3 groups and go to a board.
Sounds like the
Right squad.
I'll give you several markers per group. There's no
I think it's gonna give us a new diagram.
just start with.
Can we have our diagram? What's our diagram?
All right, here's your diagrams.
It's so useful to one of those.
You guys are going to do the vertex correction. You guys are going to do the self-energy diagram for A, and you guys are going to do the self-energy diagram for C.
So we're the bottom.
Yeah.
We have 3 vertices that's
Yeah, we start
Please remember to use the same external momentum labels that I did so that they can all be added together.
Or P5. Oh.
Huh?
I didn't help at all, that's all you.
Everybody's freaking out, and I'm gonna take the camera around.
It's okay, keys don't matter.
Doesn't really matter, but it works.
Oh, you gotta go up. So that's P1, P2, P3.
You could leave it. It doesn't matter though.
Oh, I think I see this stuff.
Yeah, you did.
There we go, there's Avery.
We gotta curve it back up now.
Alright, I did that part. Someone else.
Oh yeah, shit.
Who's Avery working with?
We fucked up a little bit.
Our equation is the sinusoid.
Alright, what is this?
Hi, Avery.